The topic of my presentation is about the design of millimeter wave passive components in semi-planar technology. The outline of my presentation is presented here. As you can see, I would start with the motivation and background of my research, and then I would talk about the slow wave structures, which is the main part of the research that I'm doing, and then I would talk about the results that I get from this concept idea that I had, and then I would talk a little about the additive manufacturing part, or the manufacturing part, and the issues that I had. And at the end, I would give a summary and the future works that I want to focus on. So, as you know, the topic of this Tesla project is about the next generation of satellite telecommunication systems. And with the satellite telecommunication system, there is always requirements for higher bandwidth, lower losses, and lower profile components. And since for me, it was already decided that where we are going to work with the semi-planar structures, I decided to also shape my whole project around this concept. And the idea of semi-planar technology is that, to find a hybrid structure between non-planar waveguides and planar printed circuit boards, where the trade-offs between these two are minimized. So with this idea in mind, I wanted to develop some kind of component that, as a final product, it would be a surface mountable component with better performance compared to what are in the market. And for the fabrication side, I wanted to use additive manufacturing, since additive manufacturing provides interesting opportunities for satellite applications. And this is mainly due to their benefits in one-part fabrication, and with the flexible production capacity and the acceleration of prototyping. So by considering all the resources and the subject topics that I have, I decided to go and work on the concept of metamaterials, which is called slow wave structures. So in general, I can say that slow wave structures are waveguides or transmission lines in which wave travels with a phase velocity equal to or less than a certain pre-designated velocity of wave propagation. And in these structures, you usually have waves travel with a lower phase velocity. And one way to create this kind of a slow wave effect inside a waveguide or inside a structure can be by creating an array of periodic structures in the propagation medium, like what you can see on the bottom left, where I use an array of pins to create these slow wave effects inside a normal waveguide. And the main advantages here is the high advantages of these slow wave structures that I'm using is the high miniaturization factor and the great out-of-band rejection performance that can be achieved. On the right, you can also see that, when the blue line would show a phase velocity of a normal waveguide, and while we're increasing the height of these pins inside the waveguide, you kind of reduce the phase velocity and you get interesting effects that you can work with. So with this idea in mind, I decided to go on and start on working, as a proof of concept, to start working on a field test. And so for this purpose, I first started by creating a resonator with these periodic arrays. The unit cell that I started with was, as you can see on the top right, it was a pyramidal pin. And I started investigating about the first mode that can resonate inside such a resonator. And as you can see, the electrical field distribution would more or less imitates the same TE101 resonating mode inside the resonator. Therefore, with the same equation and by considering the slow wave factor of the structure, you can kind of use the same equation to realize the same size of the resonator that you want. And the results would be quite similar. And the miniaturization can happen and by changing this phase velocity inside a structure. So in other words, in simpler terms, by just increasing or decreasing the heights in relation to the total height of the cavity, you are kind of reducing the size of the resonator that you have. So in some of the prototypes, as an example, in some of the prototypes or resonators that we had, we could have achieved miniaturization up to 1/4 of the size of the normal resonators. So around 75% size reductions. This was one thing that we were looking into. The other thing that we wanted to use from these slow wave structures was the out-of-band rejection. The out-of-band rejection, if you kind of simulate the propagation constant of a single unit cell in the irreducible beryllium zone, you kind of see this modes that are happening, as you can see on the. Is there any pointer? So just a second. As you can see here, so the first mode would look like this, and then you will have a band gap or a stop band in here, and then you have the other modes. My plan was to kind of design the unit cells in a way that I can enhance while I'm designing my main component in the area here, in the green area that I designed here in this frequency. I also wanted to enhance the out-of-band rejection that was created by these structures in here and try to optimize this. So as an example for a two-pole filter, as you can see, the frequency response of a two-pole filter, a simple two-pole filter is shown on the left, where we have the pass band in here at the center frequency, and we wanted to kind of remove all of the unwanted spurious bands in here. So what we did was to try and design an array of these cells or a waveguide with these cells, so that the band gap would exactly match the area that we want, and we could with this method we could achieve the out-of-band rejection in the designated area that we want. And as you can see with the slow wave filter, we had really good out-of-band rejection without any disturbance in here, as you can see on the right picture. So this is also the benefit that we want. In here, you also can see this some of these spurious bands that already existed, but this wasn't the target, and this can be removed with the higher order filters. This is only a simple two-pole filter as a demonstrator. So we decided, with filters for satellite applications, the out-of-band rejection is not the only thing that we want, and we also need, parameters like high Q factor and low losses and highly selective responses. And this was our aims. So unfortunately, I can say that slow wave resonators, in comparison to conventional resonators, would have lower quality factor, and this is kind of a trade-off between what you want to achieve with these resonators. However, we still can manage to achieve highly selective responses. And one thing that I was doing my study in was to try and find some solution for the negative coupling within these structures to implement highly selective filters. And we managed to publish the results of this study in a recent paper published in a recent conference. And what we designed was a 4-pole inline configuration filter. At the beginning, we designed a 4-pole inline configuration filter at K-band with the response that you can see here. And that was the initial design. Then we decided on how can we add negative couplings. So we designed 2 different concepts for the negative couplings that we wanted to achieve. And these 2 negative couplings are one was implemented through a modification into the PCB layer and through the top layer and through these holes and SIW line here. And the other was through a GCPW line on the lower layer to kind of create this negative coupling or these transmission zeros inside the structure. And as you can see, by implementing these 2 types of negative coupling, we kind of doubled the rule of factor of the filters that we were designing. And I also forget to mention that bottom right is the concept of this surface mountable filter that we were designing. And this is how the final product is going to look like. So this is so this was all of this was on the EM side of the structure, EM side of the study. And I did also do some study on the additive manufacturing side. The additive manufacturing that I was using was called laser powder bed fusion, which was provided by a partner company, which is called Yonim Research. They had this laser powder bed fusion, which is a metal 3D printing technology. And what I decided to use was to use this for manufacturing my components. However, I should say that this is an emerging technology which is still in development, and it's still needs some time to reach the point that we can use its full potential. So one part of my study was to study on improving both design of my structure and the process to achieve good performance, which is kind of important for me. And as you can see on the bottom left, that was the first concept of the unicells that I want to use, which was a mushroom unicell. But then I figured out that and with this 4-pole filter design that you can see, but then we figured out, like with the first round of fabrication, we found out that there are a lot of things that we need to solve before going to the next step. So I started doing some studies on how I can improve this process to achieve what I want. So my study was contained of several steps. Like I started studying like how I can do this improvement through the design for additive manufacturing rules, implementation, how I can modify the build orientation, and how I can use the process parameter optimization to achieve what I want. And through learning all of this, I figured out like how I can improve the designs that I want to achieve. And at the end, as a suggestion, I would say that like anyone who wants to use additive manufacturing would, for his purpose, he should develop first a test bench model so that they can first investigate that, how they can more effectively manufacture what they want. There are different steps and there are things that you can do, but I should also add that, the additive manufacturing wouldn't end also at the end of the fabrication. You also need to have some post treatments, and this was also a topic of my studies. And I started doing some research into this and like to figure out what post treatments are required for removing surface roughness and what are the choices and which one is more cost effective and which one is more effective in terms of performance. Like which one reduce surface roughness the most, and this kind of things. And also with some additive manufacturing, it's important to figure out like what metallization technique that you want to use. And there are different techniques, but the most interesting ones, at least for our publication, was physical vapor deposition and electroplating, which kind of produce quite good results. So I would just say it as a summary that, the initial surface roughness of this manufacturing that I did was started with the 10 micrometer surface roughness. But after figuring out the several steps, I found that with the help of experts at the UNM Research, we managed to reduce the surface roughness from 10 to 2.5 to 3.5, something in between. And we kind of removed all the defects that can happen inside with the additive manufacturing. And I also write a kind of article on how the procedures on how to exploit laser powder bed fusion for manufacturing components for satellite application, which I kind of provided as a type of guideline article in a recent publication in the IMFW 2021. So just to summarize what we talked first, obviously that using a slow wave structures is we managed to, by using slow wave structures, to fabricate a highly selective filter with good out-of-band rejection performance. And we also provided 2 suggestions on how to implement the negative coupling between the concept of slow wave structures or this surface mountable component that we are developing. And we also figured out like the slow wave structures, as metamaterials in general, provides quite interesting characteristics which can be exploited for the space application. And this is what I'm spending my time and my studies on this. As for the additive manufacturing, I would say that laser powder bed fusion also provides interesting possibilities for microwave applications. However, I would say that it's still a process in development and requires more time to reach its full potential for millimeter wave applications, since it requires more accuracy and more smoother surfaces. And as for the future work of mine, I'm planning on making deeper investigation of the possibilities that slow wave structures provides, which can be implemented for the space applications. And with this, I would thank you for attention.